So, okay, so today it's a great pleasure to welcome Ben Gripaios to speak at our Dublin seminar, our Institute seminar. He's going to tell us about differential cohomology and topological actions, and we're delighted to have him. I'll let him take the floor. You can begin whenever.
Thank you very much. So it's a great pleasure to be with you, even if only virtually. Funnily enough, both of my two previous visits to Ireland have had a virtual element one way or another. The first visit got cancelled at short notice. It was because of a different pandemic. That was foot and mouth over 20 years ago. I don't know if anybody remembers that.
Wow, yes.
And then the second visit, I actually made it to Ireland. And the purpose of the visit was to play in a rugby match against Trinity College Dublin in that wonderful sports ground at the back of the college there. And when we woke up on a Saturday, the pitch was completely frozen. And so I found myself in the bar, the match was called off, found myself in the bar already at 11 o'clock drinking Guinness. So it wasn't a particularly productive visit, but it was a very enjoyable one. And suffice to say, I just hope that by the end of today's virtual visit, I'll be a little bit more comprehensible than I presumably was at the end of that one. So here we go. The title, as Denjo just said, is Differential Cohomology and Topological Actions. I'm going to describe some work which is being written up right now with Joe DeVigi and Oscar Randall Williams. And the outline will be as follows. I'll start by talking about what the goal is, and I'll spend quite a bit of time actually talking about the motivations. And then I want to talk about some specific examples of topological actions. And I'll discuss the examples really using a sort of ad hoc approach, the way it's always been done. And the reason for doing that is basically because I want to avoid introducing this mathematical beast, differential cohomology, for as long as possible. And the reason I want to avoid that is because it does involve a bit of mathematical sophistication, but also because I think by seeing the way that the examples are usually done, then you'll come to appreciate the fact that there ought to be a better way of doing it. And the better way of doing it will be using this gadget, differential cohomology. And like I said, it is a little bit involved mathematically, but if you know what a differential form is, and if you know what a fiber bundle is, then you already know more than enough to be able to process most of this talk. So let's start then with the goal. The goal is to construct and hopefully perhaps even classify topological actions which can arise in quantum field theory. And I'd like to do that both without any symmetries at all, but also in the presence of either global symmetries or local symmetries. So to explain the setup, what's a quantum field theory? Well, you start with some space-time, which I'll take to be a manifold M, dimension n. And throughout this talk, I'm going to be working in the Euclidean picture. And so by the usual arguments, I'm going to take M to be a compact manifold without boundary. And then my quantum fields, or my fields, they're just going to be smooth maps, which I'll denote generically by F, to some target manifold. And that can be any sort of manifold you like, and I'll call it X. So sometimes I'll call space-time the source, sometimes X the target, and I hope there won't be any confusion. And basically the goal is going to be to construct topological actions. And what that means is I'm only going to allow myself one more piece of structure in this setup. And the piece of structure I'm going to allow myself is I'm going to allow the manifold M to have an orientation on it. So there won't be a Riemannian metric or Lorentzian metric. There won't be any spin structure. The only thing I've got is an orientation. And the reason I want to let myself have an orientation is because basically it's quite difficult to build actions at all if you don't have that basic ingredient. For example, most of us think of an action as the integral of a Lagrangian. Well, you can't do an integral on a manifold until you've got an orientation. But what we'll see is as long as you've got an orientation, you can get quite a lot of interesting stuff. And so that's going to be the goal. And then we come on to the obvious question of why do I want to do that? What are the motivations? And I'd like to split those into two parts. There'll be the sort of lowbrow motivations, which I'll discuss first. And then there'll be some more sort of aspirational highbrow ones, which I'll come on to later. So let's start with the lowbrow ones. The lowbrow motivation is that topological actions are basically everywhere in physics. And not only are they everywhere, but also they have very interesting physical phenomena associated with them. And so I think it's important to realize topological actions are everywhere because even though most of the time in physics we're interested in theories with much more structure on space-time, in particular a metric, that doesn't preclude you from including terms in the action which don't rely on that structure, namely topological ones. And that's sort of an instance of Gell-Mann's totalitarian principle. Everything which is not forbidden in quantum mechanics is compulsory. So if you can include, if something's allowed in the action, then you should stick it in there. And so even though most of the time we're interested in non-topological things, topological actions still got an important role to play. Here's the simplest example of a topological action that I could think of. If you start with a rigid body like a tennis racket, then, well, let's see. A tennis racket is made up of fermions, made up of protons, neutrons, electrons. Now imagine about half the time a tennis racket gets made, the thing in itself, overall, is actually a fermion. Fermionic tennis racket. And I imagine the other half of the time, it's a bosonic tennis racket. And certainly, we probably all agree that isn't going to be anything else. Okay, now, so what? What's this got to do with topological actions? Well, one way you can think about the motion of a rigid body, you can think of what's the configuration of a rigid body? Well, it's just its orientation relative to, say, where it started at time 0. And so you can think of it as particle motion on the manifold, which is SO3, which is the group of rotations. And I claim that there must be a topological action in this setup. Why do I claim that? Well, if your tennis racket is a fermion, and if you rotate it by 2 pi about any axis, then whatever the action is in this particle description, it better have a factor of pi, or equivalently a factor of -1 in the thing which is physical, the exponentiated action, to take into account the fact that that thing is a fermion, not a boson. And why must that be a topological action? It has to be a topological action because it doesn't matter whether it's a tennis racket, a potato, whatever. In principle, they could presumably all be fermions, and so you need to be able to write it down for any kind of rigid body. And so there is actually a topological action which corresponds to this effect. It's not that easy to write it down, but you can certainly do it. So that's the simplest example that I can think of a topological term. And I claim that topological actions are important. Well, if you agree that the difference between fermions and bosons is important in physics, then you have to agree that topological actions are important as well. Okay, so that's the first example, but if I look a bit deeper into physics, I can find examples all over the place.
Sorry, example, can I ask a question about your example there?
Of course you may, please do.
If space-time doesn't have a spin structure,
yeah,
can you even define a fermion?
Well, the point is, in my description, I don't have a fermion, but I need a term in the action which is responsible for which can capture the fact that that thing behaves like a fermion. It's another good example is the Skyrm term in QCD, right? You can describe baryons using skyrmions, and there's a topological term in the action which does the job. This was first mentioned, I think, by Witten, which does the job of giving you the -1 when you rotate the skyrmion by 2 pi.
So the fermion in nature is really in the SO3, it's in the target manifold rather than the base, is that right?
There's a term in the action written on the target manifold which gives you -1 when you rotate by 2 pi.
Yeah.
Right? And it's I mean, your question is actually interesting because I think it gets to the heart of what a lot of this talk will be about. In physics, we're often in a situation where you start at high energies with some description, you pass to low energies, you get a completely different description. This is certainly not a description in terms of the protons and neutrons in the tennis racket, right? But you still have to be able to capture the effects at low energy, which you know to be there at high energy. And the way it's being done here is with a topological term. Okay? All right, here are some more examples. If you take any particle motion in an electromagnetic field, then that's also, the interaction with the electromagnetic field is a topological term. It's not totally easy to see that when you write things the way physicists do. You'd say, oh, well, the interaction term is something like, I take, say, coordinates x mu, I differentiate with respect to the world line parameter, and then I couple that to a mu. There are some mu's in there, and you start to worry, well, maybe it depends on the metric. An easy way to see it doesn't is just to write it the way a mathematician would do it. The right thing to do is your gauge field, in this case, is just a 1 form on the target. You can pull that back along the map, which I'll call x, to the world line and integrate it. And these are the same thing. And the fact that this thing didn't require me to even mention coordinates at all tells you that it's a topological invariant. And so some of the examples that we'll discuss today, they will actually be interesting examples of particle motion in electromagnetic backgrounds. We'll have things like particles moving in solenoids, the Aharonov-Bohm effect. We'll have things like particles moving in the background of the Dirac monopole. And they will all be good examples of topological actions in a very simple setup, just in quantum mechanics. Okay, there are plenty of topological actions when we move from quantum mechanics to quantum field theory. Already, if we look in the real world, if we look in the strong interactions, then there are two interesting and important topological terms. One of those appears in the low energy effective chiral Lagrangian description of mesons. And that's the famous Wess-Zumino-Novikov-Witten term. Somehow the job of that term is to reproduce the anomalies which come from quarks in QCD, the high energy description. More about that later. The other topological term in the strong actions is in QCD, the high energy description. Even if you throw out the quarks, you have the pure gauge theory, then you have this famous theta term, which is topological, and has interesting effects, the strong CP problem, the eta prime paradox. Any classification of topological terms, like the one that I want to put forward today, has to be able to capture this, and this, and this, everything, basically. Going further, even if I look at pure gauge theories not in even dimensions, like in the real world, but say in odd dimensions, then there are topological terms in the form of Chern-Simons actions, and they have an important role to play in the physics, condensed matter, quantum Hall systems. And then much more recently, there's been an explosion of interest in the condensed matter community in so-called symmetry protected topological phases. And again, behind what's going on there is really topological actions. And the same is true for any anomaly in quantum field theory. The modern understanding is that any anomaly in quantum field theory can be understood in terms of a topological action in one dimension higher than the one you're living in. And so again, if you can get a classification of topological terms, which is what we're hoping to do today, then you've got a good handle on describing all of these sorts of things. Okay, so I've given you many examples, and if you know about those examples, and I'm sure many of you do know about the different examples, you'll know that there are lots of different constructions. There doesn't seem to be any kind of unified construction of topological terms. They're very much ad hoc. And when you view the situation like that, it's very hard to imagine how a classification could be possible. But there are three sort of small clues that might make you think that nevertheless, it is possible to make some sort of classification. So here's the first clue. The first clue is if I go to the simplest case of a quantum field theory, not even quantum mechanics, which is one space-time dimension, but zero space-time dimensions, then a classification is easy. So what happens in a naught-dimensional quantum field theory? Well, space-time is just a point, or a finite disjoint union of points. And then your degrees of freedom are just going to be maps to any target space you like, X. And so really all the information in here is basically where you send a point. And so the complete set of degrees of freedom of the theory is really just the points at X. Now, how can I get topological actions from here? Well, remember, a topological action, or rather the physical thing, which is the exponential of the action. By the way, I much prefer units in which h bar is not 1, but h equals 1. And that's because that means it's special when the action is an integer. So I'll always work in these units with a 2 pi out in the front. So what is an action or an exponentiated action? Well, really, it's just an element of the group U1. So here's a way to build a load of topological actions in a zero-dimensional theory. You just take the manifold U1, and if you take any map, call it G, from X to U1, that gives you a topological action. You take your point, space-time, you see where it goes, you compose it with the map G, you get an element in U1, and you call it the action. And in fact, they're the only actions you can get topologically. And so the classification is easy. It's basically the space of smooth functions from X to U1. So if classification is possible in dimension 0, you start to wonder whether it might be possible in dimension 1, 2, 3, and so on. So that's the first clue. The second clue is that if you go to any dimension, the set of possible actions, the set of possible actions is not just a set. It has the structure of an Arbelian group. And that sounds very highfalutin, but the argument behind it is just this. If you take two actions and add them together, you get another action. And so you have an Arbelian composition law, and similarly, it's quite easy to argue, for example, if you reverse the orientation, then you get an inverse action. And so the fact that the space of actions has got the structure of an Arbelian group means you can do algebra with it. And even better, the fact that this really is encoding some property of manifolds or maps of manifolds from one to another, space, time, and target, means that this is really a question, this classification question is a question about taking geometry and topology and turning it into algebra. And that, of course, is exactly what algebraic topology does for you. And so the hope is that you can bring the not inconsiderable arsenal of tools that have been developed in algebraic topology over the last 70 years or so to bear on this problem. And as we'll see, that's exactly what happens in the classification. So that's clue number 2. And well, let's just see it actually happen in practice. In the rigid body, I said that there should be 2 topological actions, if you like. There's the one which is 0, that's the one for the boson, and there's the one for the fermion. So there's a set with 2 elements, and in fact, they form the Arbelian group Z over 2. If you take, for example, a particle moving in a plane in a uniform magnetic field, then you get, of course, the famous Landau levels. What are the possible values of the magnetic field? They correspond to the different space of topological actions, where you take any real number. So you get R, that's also an Arbelian group. If you take a particle moving in a solenoid around a solenoid in 2 dimensions, that's the Aharonov-Bohm effect. Then there's an Aharonov-Bohm phase, which classifies the different actions. You get R over Z, it's also an Arbelian group. And then finally, for the Dirac monopole, as we'll discuss in gory detail in a moment, there's a quantized charge, as Dirac famously showed, and so the space of possible actions is isomorphic to the integers, and lo and behold, every single one of those has the structure of an Arbelian group. In fact, it goes even further, every one of them has the structure of a Lie group, but let me not say anything more about that for now. It's also worth noting, you can basically get every type of Lie group. You can get torsion, you can get things which are totally disconnected, you can get tori, and you can get the real line. So you can actually get every kind of Arbelian Lie group is the space of some set of topological actions. All right, and then clue 3, I sort of already gave it away right at the beginning. Clue 3 is that all of the constructions of topological terms which exist so far are basically ad hoc. You take a particular physical system and you think about, well, what can I do? What sort of forms have I got on my space? And you make an ad hoc construction. And the hope is that if you find a universal construction, namely one which works for any n, f, and x, then you hope that maybe the classification will be much more straightforward. Okay, and so the hope is that it may be possible to do a classification. And once you've got a classification, not only do you get a much better picture of where topological terms come from, but you can also start doing real physics with them. And I think the nicest example of that comes from the parallel with the Wess-Zumino-Witten term, Novikov-Witten term in the strong interactions. Because there's a beautiful story there. And the beautiful story is that QCD at high energies has got quarks. The quarks, at least in the massless limit, have chiral symmetries. We know that those symmetries are anomalous because we can do calculations in QCD. An argument due to a 't Hooft says that those anomalies have to be reproduced in the low energy theory. And the job, if you like, of the Wess-Zumino-Novikov-Witten term is to reproduce those anomalies. So at low energies, even though you have a theory of Goldstone bosons, or effectively mesons, there are no fermions in there at all, but you still have to reproduce the anomalies. And the way you do it is with this term in the sigma model action. And so this thing can be generalized. Once you've got a classification of topological terms, and once you've got a classification which can tell you which ones are allowed with or without both global symmetries and local symmetries, then you can ask which global symmetries could be gauged at low energy. And so you get a much more powerful handle on this idea of understanding strong dynamics via anomaly matching. The way we used to do it is you look at the fermions in the high energy theory and the fermions in the low energy theory, and you just compute the anomalies in two cases and you check that they match. And as you probably know, people like Seiberg had a fantastic amount of success in the 90s with supersymmetric theories by basically comparing anomalies in that way. Once you know how the anomalies, or rather terms that reproduce, topological terms that reproduce anomalies, and once you can classify those things, you can basically apply this tool in situations where there are no fermions at all at low energy. So QCD is a good example, but basically any theory which confines completely and there isn't, say, supersymmetry to force you to have fermions at low energy, well, you can still use this trick of anomaly matching to check that your low energy description really is the correct one. So this could be quite a powerful tool. And actually, as we'll see, even when we go through the examples, this is much more mysterious than you might think based on a casual inspection of this story of what happens in QCD with the Wess-Zumino-Witten term and whether you can gauge things. For example, we'll see two surprises, which I think are actually new today. One is that if you take a Dirac monopole, the monopole sits in space, the magnetic monopole, and the theory has still got rotational symmetry. And so you could say, okay, can I gauge that rotational symmetry? There's a topological action, which represents the effect of the monopole. You can ask if you can gauge the rotation symmetry. And the answer is very subtle, as we'll see. The answer is you can gauge it, but only if the monopole has a strength which is an even multiple of the minimum size of the monopole. And the reason for that is very subtle, as we'll see. And when I discovered it, I was shocked. And the reason I was shocked is that not only is it a very subtle sort of global effect, if you do the kind of analysis that Witten did in his famous paper on the Wess-Zumino-Witten term, you miss it completely. And so I was shocked, not only because of that, but I was also shocked because to me it's very odd that in quantum mechanics, there should be systems which have got sort of anomalies. Why do I say that? Well, quantum mechanics is a one-dimensional quantum field theory. And all of the local anomalies I know of, they live in even dimensional theories. So there's a sort of already a mystery to be understood, which I hope to do in the future, which is basically there are terms in quantum mechanics which have topological actions where you have global symmetries which you can't gauge, and I don't really understand why. And so I think there's a lot of things, a lot of potential to learn some new things by studying these systems. So that ends the sort of lowbrow motivation. So perhaps I stop and take some questions if there are any.
Just from, can I ask maybe just, can you say more on that quantum mechanics? Because I didn't quite catch what the essential feature was. You're saying that it has to be an even multiple of the basic monopole charge, but
yeah. So Dirac gave you this condition that the thing had to be quantized in the first place, right? And so depending on what you say the electric charge is, so the physical system here is as following, to be completely explicit. I've got my magnetic monopole, say of strength G, say at the origin in space. And then I've got a charged particle of charge E moving around it. And the topological term is basically a topological term which takes into account the effect of the monopole in the motion of the electric charge. And so Dirac's condition is something like Eg equals 2 pi, I forget what it is exactly, right? I'm telling you that if you take the rotational symmetry of this problem and you try to gauge it, then you'll actually find that Eg has to equal 4 pi in order to get a consistent theory. And I'll discuss that in much more detail later on.
You're going to come back to this?
I'm going to come back
okay,
and
all right, then that's
sort
fine.
of do it properly.
Okay.
But,
can I ask a question?
Yeah.
Oh, yeah, please.
Is a tension between SO3 versus SU2? Because if EG is 2 pi, certainly you can quantize it, but the group is not SO3.
So the an answer to your question is yes, it is about the difference between SU2 and SO3. But the reason why it comes down to that is probably a lot more subtle than you might think. But when I discuss this in detail, hopefully it will be clear where SU2 comes into it.
Okay, I have one more question.
Yeah.
From what I understood, all these problems are under the general rubric of domains of operators. For example, a particle on a circle. For a particle on a circle, okay, the domain of the say the momentum operator is given by points on a circle. Okay, and they give all kinds of things like parity and normal. So I would have claimed that all these issues that you're raising can be understood completely, can be understood in terms of operator domains. Okay? And there are many more such examples one can find, which are not, they're coming from domains of operators. So there's no metric there.
Yeah. Well, you may well be right. Actually, when I come onto my highbrow motivations in a minute, I'll see that really, well, let me come onto my highbrow motivations, and then maybe you'll see what I mean. Any other questions? Okay, so let's talk about the highbrow motivation. The highbrow motivation and why I'm interested in trying to construct and classify topological terms is because in the back of my mind, I have the bigger picture of trying to understand what this mysterious, magical thing, quantum field theory really is. And so what's the story there? The story is that in the last nearly 100 years now, we've come an awfully long way by taking this sort of ad hoc description of quantum field theory. Take, for example, the path integral, but you can take whatever you like. And we've always known that it's not well defined, but we've been manipulating it carefully. And because we've had spectacular multiple successes in experiment, we've gained a lot of confidence that somehow quantum field theory is the right tool to describe nature. And I imagine we all agree that that is true. But it's important to recognize that experiment has played a crucial role in this. And if you remember, well, perhaps you don't remember, but if you've read the history of quantum field theory, people were very suspicious of quantum field theory at the beginning because of all of these infinities which appeared everywhere. And it was only because of the repeated agreement with experiment, and sometimes very accurate agreement with experiment, that people started to think, well, actually, this thing probably is right. But I think it's also true that deep down, we all know that things like this here, they are not the right way to do quantum field theory. This cannot be the way that God does it. So what are the problems, for example? Well, firstly, this path integral is horribly ill-defined. But even worse than that, even if it were well-defined, you've got this problem, which we've got plenty of evidence for. If you consider, say, the space of Lagrangians and fields, and you imagine that there's a map from those to the space of quantum field theories, which of course there would be if this is always well-defined. Well, the problem is this map is not a one-to-one correspondence. We know, in fact, there's neither surjective nor injective. You can take multiple different degrees of freedom and Lagrangians and end up with the same quantum field theory. That's duality. And moreover, there are quantum field theories which we believe cannot be describable in terms of any Lagrangian. And so somehow, no, this is probably not the right way to be doing quantum field theory. And we sort of got away with it, at least in high energy physics, we got away with it for a long time because, of course, we had experiment to push us back in the right direction. And the problem now, at least in high energy physics, which is where I come from, experiment doesn't seem to be providing such a great guide anymore. After the discovery of the Higgs boson, we haven't found anything new. It reminds me a lot of the Michelson-Morley experiment. People were convinced that there should be some motion of the ether with respect to the Earth. They measured it, they got 0. They measured it 10 times more accurately, they got 0. And so they kept going. And the same thing seems to be happening now at the LHC. And it's sort of wonderful in a way. It tells you that you really don't understand anything at all. But of course, very difficult to take 0 and turn it into theory. And what was needed, at least in the days of the Michelson-Morley experiment, it needed somebody to go back to the drawing board, or perhaps the blackboard, and really think about what are space and time, and what are symmetries of space and time, and so on. And I think, at least if you're a high energy physicist at the moment, at least some of us need to go and do the same thing and try and really figure out what quantum field theory is. After 100 years, it's probably about time that we really figured it out. So what is the right way to do quantum field theory? If you pick up a textbook, then you might see a statement that quantum field theory is somehow the most general way to combine notions of quantum mechanics, things like superposition and probabilistic interpretation, with the notion of locality in a way which is compatible with the symmetries of the problem. And I'm sure we all agree that's probably true, but I think you need to say rather more than that. In particular, what's important in quantum field theory is that you have not just locality, but you have an extended notion of locality. And you have not just symmetry, but a notion of higher symmetry. And there's one thing which we sort of never ever talk about as physicists, because we're used right from the first year of undergraduate studies to accepting it in the first place, is this notion of smoothness. It's the fact that, what does it correspond to? It's the fact that because we're in the business of predicting the results of experiments, and because experiments only have a finite resolution, it must be possible to make arbitrarily small changes in your theory without any experimentalist being able to detect them. And so the usual way of thinking about it, I think, is that when I'm doing physics, I can, without loss of generality, replace any space I've got by a smooth space. I can replace any map I've got by a smooth map, and it's all fine because no experimentalist could tell the difference. But if you're in the business of trying to really understand quantum field theory, and in particular if you're in the business of trying to classify quantum field theories, which what I'm doing today is somehow the first step along that road, then it's not that you can take smoothness without loss of generality, it's that you have to take smoothness into account. Because if you don't take smoothness into account and you come up with a classification of theories, you're going to be double counting. You're going to distinguish two theories which no experimentalist can actually distinguish. And I deliberately pulled the wool over your eyes earlier when I gave you the classification of zero-dimensional theories. I told you that the space of functions was the space of zero-dimensional quantum field theories was the smooth functions from x to u1. Of course, a priori, I could have taken any functions I wanted to from x to u1. The point is that because I know what I know about quantum field theory and the fact that it's trying to describe experiments, is I had to put a smoothness requirement in there. And so what's important here, I mean, on one level, what I'm saying sounds very banal, but it's important to realize it's not enough to take the spaces to be smooth. It's not enough to take the maps to be smooth. You have to take everything which is observable, including the actions themselves, to be smooth. And so you need a smooth structure on a space of functions. And so this is a crucial ingredient, I think, in terms of us understanding what quantum field theory really is.
Can I just say something?
Yes, of course.
Wouldn't it, in most of your arguments and your informal ones about what experimentalists can detect, do just to say it was continuous?
Absolutely. So one of the things that we will do in this classification is, instead of insisting on smoothness of differential cohomology, we'll introduce a continuous structure on it. But again, the point is, it has to be, it depends what your approach is. If your approach is, I'm just trying to make my life simple and asking what I can do without loss of generality, then yeah, you can take non-continuous functions, continuous functions, whatever you like. If you're in the business of classifying things, then you have to work out what the right condition of smoothness or continuity is.
Now, what do you mean by smoothness? What is smooth? Because in standard quantum field theory, the fields are actually distributions. They're not even continuous functions.
Yeah, absolutely. So, I mean,
So what do you mean by smoothness?
This is exactly why I say that this is an issue which we have to figure out in order to be able to properly understand what quantum field theory is. I can certainly tell you what I mean by it in the context of my approach to quantum field theory, which is the geometric approach, which I'll talk about later, based on functors on Born categories. And there, the notion of smoothness is that everything which you thought was a category is actually a stack. Okay, so let me go on. So quantum field theory should somehow combine all of these things. And let's look at the approaches which are on the market. There are sort of three which are obvious to me. There's amplitudes, there's operator algebras, and there's this approach which I just alluded to based on geometry. And so you could ask the question, well, which of these is the right one if I want to understand what quantum field theory is? And I think that the only fair answer to that is, at the moment, we have absolutely no idea. and that we need to explore all three of them in order to see where they lead us. And a second answer is, which one of these is most appropriate depends a lot on what you actually want to do. If you're in the business of computing probabilities for protons to produce Higgs bosons at the LHC, then you have absolutely no choice but to use the amplitude approach, because the other ones, at least as far as I understand it, cannot get you anywhere near a real world computation. But if you're interested in questions like locality, then I would argue that this geometric approach is much better than the amplitudes one. Why do I say that? The amplitudes approach, of course, is based on the S matrix. That's the first thing you do. And so you're only allowed to talk about particles which come in from infinity. And so the description, if you like, is maximally local. And that's not to say, don't get me wrong, not to say that locality is not in here and not fully encoded. It just means you have to work harder to work out how it's encoded. And so if you're interested in questions about what is locality in quantum field theory, then I would argue that this geometric approach, in which it's absolutely manifest right from the beginning, is perhaps more useful. So let me spend a few moments talking about this geometric approach. So the idea goes back a long time to the 80s with independent work by Siegel, Kontsevich, and Atiyah. What's the idea? So the statement of locality in quantum mechanics or in field theory is basically that the Hamiltonian just depends on the time or derivatives of x with respect to the time. You can't put in 2 times, you can't have infinitely many derivatives, things like that. Now, if I want to get away from this Lagrangian description, if I want to do quantum field theory, quote unquote, properly, then I need to reformulate this idea. And the idea is the following. You consider the evolution of a system along its world line, and you can ask, to that evolution is associated a time translation operator. It's the thing which is formally e to the IH, but let me not write about that because time translation operator from T2 to T1. And then locality just becomes equivalent to the statement that if you want to go from T1 to T2, let me make this T3, then the amplitude to go from here to here is actually just got by composing the amplitudes to go from here to here. And these people took that idea and they lifted it to quantum field theory. And so they said in higher dimensions, you should be able to compose amplitudes. And that is to say, you should either be able to cut or to paste along manifolds of codimension 1, and things should compose nicely. And
this cobordism idea, how does it incorporate Einstein causality, which is basic to, for example, algebraic quantum field theory?
Yeah, indeed. It's gone completely because the very first thing you do is you pass the Euclidean picture.
There is a metric here. I mean, the way cobordism, are you putting a metric here?
No, I have no metric here.
So again, the question is, there is a standard notion of causality where you take quantum fields in some spatial region, they commute with the causal complement, fields in the causal complement. Where is it here?
All of that has gone. The very fact, it's gone, yeah. So this is...
So what is the meaning of causality here?
You know, normally there's something left of that that is called Osterwalder-Schrader positivity.
Yes.
So you need some kind of positivity, nevertheless, if you want to get back to normal time.
Correct. So there's a notion, or there's the notion of reflection positivity. But I mean, I hear what you're saying. A major disadvantage of the Bourdism approach is that in order to define Bourdisms in a useful way, you need to deal with compact manifolds. And the way you do that is you take your Minkowskian theory and you Euclideanize. Believe that both Siegel and Kontsevich are working together right now on a project in which they deal with this issue in the Bourdism approach. But this is an open issue.
Okay, again, why do you call this causality? Or why do people call this causality?
I never said causality.
Locality. Why does one call this locality?
But locality and causality are not the same thing.
They are related.
They're related, but they're not the same thing.
Yes. For example, how does one recover spin statistics theorems?
Mm-hmm.
Spin statistics theorems.
Yeah, that comes from reflection positivity when you turn the time axis.
Yeah.
But you need that condition. It's crucial.
Absolutely. Absolutely. But again, I never mentioned causality. I want to, the one thing that I would like to encode is locality at the moment. Causality is a related but separate thing, which also needs to be encoded, yeah. Okay, but it's not just locality, it's this notion of extended locality. And what does that mean in this picture? That means that it should be possible not only to cut along manifolds of codimension 1, but you should also be able to cut along manifolds of codimension 2. That is to say, manifolds with boundaries and corners, and paste things together consistently. And it took a long time where basically this idea of Bordism's geometrical approach to quantum field theory was in a bit of a backwater. And the reason is that if you're going to allow on the source side manifolds with corners, then you have to decide what your QFT functor is going to associate to those things. And unfortunately, it needs to associate not just categories, but categories of categories and so on. And so the problem is that this whole approach was hamstrung by the fact that even the category theorists themselves couldn't really agree on what the right definition of a higher category was. But it seems like now, and in particular, some of these works here will show the way, it seems like now that that kind of problem has been solved. So we're really in a position to discuss extended locality in this picture. And so to end the discussion about, I mean, this is supposed to be the highbrow motivation for my talk. The idea is that what I'm going to do today is going to be a very baby version of this modern geometric approach. Why is it baby version? Well, firstly, I'm only going to go down the sort of first step down the categorical rabbit hole, which is I'm just going to insist that the theory, the action, be defined on every possible manifold without boundary M with an orientation. So really, I should take the next step, which is define it on manifolds with boundary and manifolds with corners and so on. I'm just going to do the first step. And the reason it's enough to do the first step is that it's believed that at least in the theories that I'm going to talk about, which are really sort of semi-classical theories, I'm only interested in the topological actions, I'm not interested in the quantum field theories themselves. It's believed that once you define it consistently at this level, then actually this full extended locality is obeyed. So the end of the highbrow motivation is that what I'm trying to do today is really the first step in what I think is a very promising approach to really trying to understand quantum field theory, which is this geometric approach based on Bordisms. But like I say, there are other approaches available, and I think the right thing for us to do as a community is to try to develop all of them. Okay, are there any more questions? Okay, then let's go on to the next part of the talk, which is to discuss the examples. And like I said, I'm going to do these in an ad hoc way. I'm going to do them the way they're sort of done in the literature. And the idea is hopefully that you see that there are some funny things going on here, and there ought to be probably a better way of doing it. So let's start with the one which Denjo is interested in. That's the motion of a particle, charged particle in the presence of a monopole. So I've got my monopole at the origin. My charged particle's moving around. Because I'm only interested in topological effects, then I'll simplify things. I'll force this particle to live on the surface of a two-sphere. And this is something which was studied obviously by Dirac and also by Witten. But actually the history is much older. The history goes back to 95, that's 1895, and to Poincaré. And you might wonder why Poincaré was interested in magnetic monopoles, given that presumably there were just as few magnetic monopoles around in 1895 as there are today. And the reason is that an experimentalist colleague of Poincaré asked him what happens if you take a normal dipole and consider a charged particle moving around in the limit where the charged particle stays close to one pole. And Poincaré was a smart man. He realized that he could just treat that as a monopole, and he wrote down the equations of motion. Here they are here, and he solved them. And what he found is that the particle moves on the surface of a cone. And when I restrict to 2 dimensions, it lives on the intersection with the two-sphere. But let's not look at it that way. Let's look at it the way Witten looked at it. So what did Witten do? Well, Witten started from the equations of motion, and he realized that it's not possible to write down an action which reproduces those equations of motion. So let me draw a picture in terms of my setup. It's particle motion, so I've got a Euclidean world line, that's an S1. I've got a map F to the two-sphere X, and I'm trying to construct a topological action. And so what did Witten do? Witten said, well, here's an action for you. Take this world line, see where it gets sent by F, look at its image in the two-sphere, and say, here's the action. The action is the area of this disk. And so there are two remarks to make about that. The first remark is that it is not obviously well defined because, of course, like the famous mathematical joke, am I on the outside looking in or am I on the inside looking out? I could equally have chosen this area here. And there's a simple solution to that problem, which is just to insist that the total area on the sphere is an integer. And so this at a stroke explains the quantization of the charge on the Dirac monopole. And the second thing, the second remark I'd like to make is that the problem with this definition of the action, it's also maximallyalocal. And so what I'd really like is a definition which is as local as possible. So here's a definition which is as local as possible. I take the 2 form omega 2 on the two-sphere, whose integral gives me the area. And what can I do with that thing? Well, if I start with my world line, then that always bounds a disk. And because every circle on the two-sphere can be shrunk to a point, then it's always the case that no matter what map F you take here, you can always find a lift from the two disk to the sphere. So here's a definition of the action which is sort of as local as possible. The action is going to be, I take the area form, I pull it back along the lift, that's the usual pullback of differential forms, and then I integrate it over the disk. And so this was Witten's definition of the action. And can you see that this corresponds to the magnetic monopole? Well, here's one way to see it. There are two terms. If I have two terms in the action, I have the usual kinetic term, then that wants me to live on a great circle. I move on a geodesic. This action is just the area. So if I want to minimize that action, which is the classical Euler-Lagrange thing, then I want to live on a point. And so what happens, the balance of those two terms means that I live on a circle somewhere in between the two, namely the intersection of a cone with the two-sphere, and that's exactly the result that Poincaré got. So this really is the action representing the effect of the monopole at the origin. Okay, so this was all done by Witten, and it's very nice, but now I'd like to do something new today. And the thing I'd like to do, which is new, is I'd like to take the rotational symmetry and I'd like to gauge it. So let me draw the picture again. Here's my two-sphere. Here's my world line S1. And here's my map F. And what I'll do, instead of gauging this entire rotation symmetry, to make the discussion as simple as possible, I'll just pick a U1 subgroup, which corresponds to rotation about some axis. And I'll try to gauge that. And my claim is going to be that something's going to go wrong, and we need to see what goes wrong. So here we go. What's the data of a gauge theory? First of all, I have, on top of my world line, I have a principal U1 bundle together with a connection A. That's the gauge connection. And then the other thing I have is, instead of having this map F, I have a section of the associated bundle corresponding to this matter field. And a much simpler way to say that is I replace this map F by a so-called equivariant map F. What's an equivariant map? I have an action of my gauge group on the right-hand side. It rotates the sphere. I have an action of my gauge group U1 on the left-hand side. It moves me around in the fibers of the bundle. An equivariant map is just one where if you do the function, if you do the map and then a G transformation, you get the same result as first doing a G transformation and then following the map. And so that's the data of a gauge theory: a principal bundle P, a U1 bundle, a connection A, and an equivariant map F. And so now what I'd like to do is I'd like to sort of follow in Witten's shoes and try to construct an action in this gauge case. And so here's what I can try to do. I start by observing that every S1 bounds a disk. And I observe that I can always find an equivariant map which sends it to the sphere. But now I've got to do a lot more lifting. I've got to lift this map. I've got to lift the bundle from a bundle over S1 to a bundle over the disk. And I have to lift the connection. Now, all of those things can be done. And the reason that all of those things can be done is that basically all bundles, all circle bundles over the circle are actually trivial. So this total space here is just a torus. So it looks like nothing could possibly go wrong here. But you have to check carefully that no matter which lift you choose of the bundle, the connection, and the equivariant map, you have to check very carefully that they all give the same definition of the action. And the definition of the action, by the way, at least if you follow Witten, is you just take this integral that I had before, you do the usual thing that physicists do. Wherever you see a derivative, you replace it by a covariant derivative. The whole thing turns out to be not invariant because it's a topological term, but you add some pieces and you correct it. And if you did that, if you did exactly what Witten did for QCD, but on this example of the monopole, everything looks fine. But it isn't fine, and here's why it's not fine. The problem is you have to check that it's independent of all of the lifts, and subtle things can happen, global things, when you lift bundles in different ways. In particular, there's a lift which corresponds to sending the thing here. And there's another lift which corresponds to sending the thing here. And you can express the difference in those two lifts in terms of a U1 bundle over S2, basically by sticking the two disks together. You have to be very careful that even if you take two trivial bundles and glue them together, the result you get is not necessarily a trivial bundle. And in particular, there is a way of choosing all of these lifts here. I'm not going to do it now in detail, which ends up giving you a result which is a non-trivial bundle over the two-sphere. Which bundle is it? It is actually the bundle SU2. So there was a question earlier about whether this was connected to the difference between SU2 and SO3. It is, but only in the sense that SU2 represents the Hopf bundle, which is the first non-trivial bundle of U1 over S2. And when you follow all of this through, you find that because of this dependence on the lifts, you get an ill-defined answer when the magnetic monopole charge, which is really the size of the term you started with here, the normalization of this term, you get an ill-defined answer when that's odd. And like I said,
sorry, I will interrupt again.
Please.
We have done some work on this kind of idea, but the two form omega,
yeah,
to start with, is an integer cohomology. That's what you were telling before. No?
Absolutely, yeah.
Okay. So there is a standard theorem that you can pull it up to the U1 bundle and write a one form. Okay, because after you pull it up, it is an exact form. So then the action can be defined simply by integrating over the circle, integrating the circle, the one form over the circle. Then one can gauge it. I don't see the problem there.
Ah, well. So what did you say again? I should take the two form, omega 2, which lives on S2. Yeah.
So you pull it up to the U1 bundle.
How do it lives on S2. How do I pull it up?
No, pull it up. No, originally you are given the two form, which is defined on the disk. Okay? Which is
no, sorry. I have a two form, which is defined on S2. That's the area form.
Okay.
Yeah.
You have two form here, which is defined here.
Yeah.
Then because it is in the integer cohomology, okay,
yeah,
there is a U1 bundle, which in this case can be taken, for example, to be S3. Okay?
Yeah.
And you can pull up this form to S3.
Yeah, sorry, you're absolutely right. Yeah, the problem is you need to make this construction for every possible connection.
Wait a minute.
It's a gauge theory.
Let me finish. So
yeah.
the two form on S3 is exact. So one can write it as a D of the pullback can be written as D of a one form. Okay? Yeah. It's a Maurer-Cartan form, component of a Maurer-Cartan form. So I simply integrated over the original action I rewrite as integral over the circle here, not on the disk, but on the circle. Then I gauge it, I pull it back here on the circle and I gauge it. I don't see any problem.
It's a little bit difficult for me to follow what you're saying because of course I'm not able to see what you mean with the different things. But well, perhaps we can come back to this later. But I'm fairly confident that there is a problem here, and perhaps the easiest way to say that I'm fairly confident is when I do the classification at the end. This obstruction will correspond to a very clear statement in equivariant cohomology. Okay, so let me go on. Let's do another example. So this example, the example I just discussed, is actually quite difficult to follow because of this whole confusion about gauging fields and so on. Let me give an example where there's a problem with even having a global symmetry. And again, the problem is due to lifts. So the problem now is you have a particle moving in 2 dimensions in a uniform crystal, in the background of a uniform crystal. And the topological term I'd like to have is just have a uniform magnetic field sticking out of the plane. And so that all sounds very reasonable. How can I think about this topologically? Well, because I have a uniform crystal, I can think of the particle moving on the surface of a torus. And so my setup is I have S1, particle motion, and I have a torus on the right. And I have a map, which tells me where the particle goes. And so again, I'd like to ask, is there a topological action? Now, if I try to follow what Witten did, I immediately hit a problem because even though my circle is bounded by a disk, unfortunately, there are choices for F, in particular, if I choose my S1 to wrap a non-trivial cycle in the torus, then unfortunately, there is no possible lift of the disk to this thing which bounds. Okay, so I can't do the construction of Witten. So then Weinberg and Doka, who considered this kind of situation in general in terms of sigma models, they made the following suggestion. They said, well, you can still define an action in this way. What you do is you define an arbitrary phase associated to one cycle. Let's call it S0. And then you can define the action for any other cycle simply by adding the integral of the area form on the torus over the area, which is the difference between the two. And so they said, you can take this to be the definition of the action. And they went on from there to make a classification of Wess-Zumino terms in such models. And here's the problem with this construction. The problem with this construction is it's not automatically invariant under the global symmetry, which corresponds to translations on the torus. So you end up with a very funny situation, which was first noticed by Manton in the 80s. If you take a particle moving in a crystal in a uniform B field, classically, it's totally clear that everything is invariant under translations. When you study the quantum mechanics of that system, it's not translation invariant. And the way Manton showed it is he just computed the wave functions of that system. It's after all not very complicated. And he showed that they don't have the right invariance property. But we can see it in a much easier way. If you take this definition of the topological action, the problem is if you do a translation, if you do a symmetry transformation, then you move this fixed cycle that you picked out in the first place. You move it over here. And so there's no guarantee that this definition is actually invariant under the translations. And in fact, if you look at it more carefully, you see it's not possible to make it invariant. So in fact, this classification that was made by Weinberg and Doka actually fails in this situation because you simply cannot make a lift which is compatible with the global symmetries. Again, we see another example where a very simple system and actually funny things happen with topological actions when you try to either make them globally or locally symmetric. And I'd like to discuss one more example. The last example is even simpler. It's the one that corresponds to the Aharonov-Bohm effect. So I have a particle, world line S1, and it's going to be moving in the plane in the presence of a solenoid, say at the origin. And again, because I'm only interested in the topological effects, I'll force the particle to live on a circle. So actually my setup is just maps from a circle to a circle. And again, I'd like to ask the obvious question, what are the topological actions, firstly? There's a symmetry which corresponds to rotation around the axis. And so I can ask, what are the topological actions which are globally symmetric? And I can also ask which are the ones which are locally symmetric. So let's do all of that quickly. What about topological actions full stop? Well, here's a straightforward construction. you can make an action by taking any one form you like, omega-1 on a circle. You can pull it back along the map, and you can integrate it over the world line. So here's a topological action. How many of these actions are there? Well, it looks like there's a lot because there are a lot of one forms, but every one form on the circle is closed. If you take an exact one form, then it will give you an action of 0 because you're integrating over a closed manifold. If you take an integral one form, that is to say one whose integral all the way around the circle is an integer, then you'll also get, well, you won't get 0 for the action, but you will get 0 or 1 for the exponentiated action. And so the full space of actions, in fact, is just R over Z. It's the Aharonov-Bohm phase. Okay, so that's interesting. What happens if I try to gauge this rotation symmetry? So now I've got to add on all my data, have a U1 bundle over the torus, principal bundle with a connection A. I ask myself, which actions can I make with this extra data? And so here's something you could do. If you had a section of this bundle, then you could just take A, which is a one form on the torus, and you could put it back and you could integrate it. So you could take an action, which is the integral over the world line of the pullback along the section of A, and you could try to put any constant you like in front of that. And sections certainly exist. And even better, you've actually got a section for free here as part of the data, because I've told you there's a map from S1 to S1. Well, I can just use that map, not going over here, but going up here to make a section of this bundle. So I can take the section which corresponds to F, and this thing is a topological action. And you'll find that you can get different values of the action for every possible real value of K. So that tells you that the space of topological actions in the gauged case is just a real line. And you might wonder, well, hang on, why can't I add in these actions from the ungauged case before? The point is, if you add those in, add in the ones from before, well, you're just adding some special one form to an arbitrary one form. You don't get a new action. So in fact, the complete space is R. And there's one more thing I'd like to calculate. I'd like to calculate what is the space of pure gauge actions in this case. If I throw away everything over here, so I just have a pure gauge theory, what's the space of actions? Well, the arguments are almost exactly the same as before. The only thing now is that you don't have a privileged section, and so you can define an action as the integral of the pullback along a section, but you need to check that you get the same answer for every possible section. And if you choose a section which is the constant map, or if you choose a section which winds once, then you find that they will only agree in the action if this constant out in front is an integer. And so here are three results. The ungauged theory has got actions in R over Z. The gauge theory has got actions in R, and the pure gauge theory has got actions in Z. This is the famous quantization of the Chern-Simons action. This is a one-dimensional Chern-Simons action, basically. And why is this interesting? Why did I want to talk about this example? Well, nothing goes wrong here, but the interesting thing is when you take the ungauged actions and the pure gauge actions and you put them together to see what you get in the combined theory, well, you get a funny thing. It's not that you get a sum of the two. It's not the case that R is isomorphic to a direct sum of the ungauged plus pure gauge. What you instead get is that the R sits in a short exact sequence between the pure gauge theory, let's call it P, and the ungauged theory without gauged fields. And so you see there's again, it's a nice result. In general, if you add pure matter theory to pure gauge, you don't just get the sum of the two. And in fact, it's much more complicated than this, because if you go back to our example of the solenoid, what happens in the solenoid, in the monopole example, what happened there is in the ungauged theory, I had all of the Dirac monopoles. In the gauged theory, I claim I've got half as many, the ones with even charge. And therefore this map is actually multiplication by 2. And so it's not true anymore that this fits in an exact sequence, short exact sequence, like the other one. And the conclusion from this is that when you have topological actions, there's no sense in which you can think of the thing which a priori is obviously true, that you can combine the pure gauge theory and the pure matter theory to get the combined theory. It just doesn't work like that. It's much more complicated. And actually, once we introduce differential cohomology, we'll see that you can work out what the answer is, but it requires you to go a lot more complicated things than this. Okay, so the whole point of this example section is that funny things happen when you do these ad hoc constructions. And so you wonder if there's a better way of doing it, and the answer is the better way of doing it is to use this gadget called differential cohomology. So are there any more questions before I come to this last part of the talk? Okay, so let me go on. So what I'd like to do is I'd like to try to get a universal construction of topological actions. I'd like to take any m, any x, and produce all of the topological actions in that theory. And the right thing, and if I have a global symmetry, that's to say if I have a group G acting on the manifold, then I'd like to take the subset of ones which are invariant. And if I want to make that a local symmetry, then I'm just going to add a G bundle for the gauge group G over my space-time and a connection. I replace the map by an equivariant map, and I look for the invariant actions. So that's basically all of the data. And then the question is, what's the machine which computes the topological actions? And the answer is the machine is something called differential cohomology. And differential cohomology has been around for a long time. It was first introduced by Simons and Deligne. But it's developed a lot in the last sort of 5 or 10 years or so. And here's a definition. This is most definitely not the definition which you'll find if you go back to the 70s. This definition is also from Simons from 2007. And it's an axiomatic definition. And the reason I chose this definition is it looks nasty, but actually it's the simplest one. In particular, it only involves objects which you can read about in Nash and Sen, as it were. So for example, it involves things like the integral cohomology of the manifold X, the target space, and it also involves things like the differential forms on X. So what's the definition? The definition is as follows. Differential cohomology, which is H with a hat on top, is a thing which lives in the middle of a commutative diagram. Commutative diagram means it doesn't matter which way you go, following the maps, you get the same result. It fits in the middle of a commutative diagram involving all of these objects. And what are these objects? It's just ordinary cohomology with a variety of different coefficients, integral, real cohomology, cohomology with coefficients in U1. And on the bottom, objects involving differential forms, or rather subgroups of differential forms or quotients of differential forms. What are these things? Along the top, you've got a long exact sequence, which is the so-called Bochstein exact sequence, which corresponds to the fact when you take a short exact sequence of the coefficients in cohomology, then you get a long exact sequence in cohomology. This is the long exact sequence. And downstairs, you get another long exact sequence. This goes on forever. This long exact sequence is basically a rewriting of the Dirac theorem. It's a relation between differential forms and real cohomology. And the definition of differential cohomology is it's the thing which sits in the middle together with two maps in and two maps out, such that this whole thing commutes, and such that these diagonals here, the two diagonals, are themselves short exact sequences. And so you may know that a short exact sequence already tells you what the thing in the middle is up to an extension problem. And the fact that there are two of these sequences here, and the fact that they have to fit in this, fixes this thing in the middle completely. So this is a definition of differential cohomology. So that's good, but it looks a long way away from topological actions. So let me now try to tell you how you can take this thing and get topological actions. And the construction is actually quite straightforward. So here you go. My claim is that if you take an element in this Arbelian group, it will define for you a topological action. And so here's how it goes. You take your element H, it's in the differential cohomology, and this is crucial, it's in degree 1 higher than the space-time dimension that you're living on, okay? You take your element H and you can pull it back along the map f x to n. So that gives you an element f star h, which lives in the differential cohomology, a degree 1 higher than your space-time, living on your space-time. Now, why is this a useful thing to do? This thing, differential cohomology, according to the definition, it's got two maps out. The one map out is to differential forms of degree n plus 1 on an n manifold, well, they're all 0. And the other map out is to the integral cohomology of 1 degree higher on n, that's also 0. And these two, remember, were short exact sequences. That means if these things are 0, then these two maps going in actually are isomorphisms. And because they're isomorphisms, they have inverse maps which go the other way. And so you can take your element f star h, you can follow the map going backwards. I think I called this one j, so let's call this map j minus 1. Sorry, I called it I minus 1. And you can obtain a unique differential form of degree n. So let's call it I minus 1 f star h. All right, well, if you integrate an n form over your original spacetime manifold and take e to the 2 pi I h of it, well, that's an action. And so the amazing thing is that in this way, you can basically get all or almost all topological actions. So this was the case, ordinary differential cohomology, where there are no symmetries at all. I've defined it algebraically. It actually has a very simple interpretation. This algebraic object, differential cohomology in low degrees. In degree 0, it's just constant maps. In degree 1, it's smooth maps from x to u1. That agrees with my classification of topological terms in space-time dimension 0 earlier. And in degree 2, it's still something which is quite simple. It's basically just differential cohomology in degree 2 tells you all of the possible u1 principal bundles that live on your space x with a connection. And that's why I said at the beginning, basically every electromagnetic field in quantum mechanics corresponds to a topological term. But now I can turn that the other way around. Every topological term in quantum mechanics corresponds to an electromagnetic field. Okay, what happens now when we try to include symmetries in the picture? If we want global symmetries, then we need not just ordinary differential cohomology, but an invariant version of it. Unfortunately, this didn't exist in the literature when we were doing our project, so we had to define it for ourselves. The definition is simple. You just take when G acts on your manifold X, then there is an induced action on cohomology, on differential forms, and on differential cohomology. And so you just take the invariant subgroup. And so that's a definition, just take the invariant subgroup. The difficulty, of course, is you'd like to actually compute this thing. And so to compute this thing, you need a characterization. And here's the story. This is, you get a diagram which looks exactly the same almost as the one I had before, except that I've taken the invariant subgroups of all of these things. Now here's the problem. Taking invariance is a functor, but the problem is it's only a left exact functor. And that means that where you had short exact sequences before along the diagonals, they are not short exact sequences anymore. They fail to be exact on the right-hand side, which means that these two maps out, which previously were surjections, are not surjections anymore. Now, what has that got to do with our example of quantum mechanics on the torus? Remember, what happened on the torus was we tried to make an ad hoc construction of an action using a differential form, but it didn't work. And this is exactly what this diagram is telling you. It's telling you that the topological actions, which is secretly just this thing here, they do not surject onto the differential forms of degree 1 higher, degree 2 in quantum mechanics. There are differential forms which do not correspond to a topological action. So the example of the torus is actually very simple to explain once you have this diagram. Let's look at gauge symmetries. When you want to classify topological actions with gauge symmetries, then the right thing is something called equivariant differential cohomology. That's existed in the literature for a couple of years now. Here's the definition. Again, it's axiomatic. It looks exactly the same as the one before. The only difference is that I've replaced all the objects before with their corresponding equivariant objects. So downstairs, we have equivariant differential forms, which are quite well known in the physics literature, because they play a role in supersymmetric quantum mechanics. Upstairs, we have the equivariant cohomology of X. And why does that make sense? Well, at least if G acts nicely on your manifold X, then the equivariant cohomology is identical to the cohomology, ordinary cohomology of the orbit space of X. And this fits with our understanding in physics that gauge symmetry is really a redundancy. You should just identify all the points which are connected by gauge symmetry and say the physical thing is this. But if G doesn't act nicely on X, then this thing is rather more complicated. And so again, this is the axiomatic definition. These are all things which they look nasty, but if you know enough algebraic topology, you can always compute them. And it's exactly by studying diagrams like this that you can see explicitly why the Dirac monopole case cannot be gauged without having to go through an unpleasant ad hoc construction. It's simply the statement that the equivariant cohomology of SO3 acting on S2 with coefficients in the integers in degree 2 maps onto the normal cohomology. And whilst both of those things are isomorphic to the integers, the map is actually multiplication by 2. And so again, the statement is this: there are things which live down here which do not actually correspond to consistent topological actions. Okay, I've already gone on for far too long, so let me just quickly do an example and then I'll summarize. Let's take the simplest example of all. And really the point here is just to show that you can actually make calculations using this beast. If I choose my target manifold to be a point, basically no information at all, then I'm just doing pure gauge theory. And what happens in that case is that this complicated looking diagram collapses completely. And if you go to even dimensions, you'll find that the space of topological pure gauge theory actions is obtained by computing the cohomology of something called BG, the classifying space in one dimension higher. That is a famous result due to Digraph-Witten in 1990. If you've read the Digraph-Witten paper, you'll see it took them a lot longer to derive that result than what it just took me. And if you go to even dimensional gauge theories, you'll find that the classification is again in terms of the classifying space, but involving different coefficients. And these are exactly all of the theta terms that you can get in even dimensional gauge theories. And I've never seen this written down in a physics paper as a classification of even dimensional gauge theories, but it's pretty obvious when you think about it. These are roughly just the characteristic classes. So actually you take this complicated looking object and you quite quickly get results which are very general and very wide applicability in physics, but they're easy to get. Okay, and the last thing I wanted to say is that you can study, again, using algebraic topology, the maps from the equivariant version to the invariant version. And that's exactly the thing you need to do to be able to ask the question of which symmetries can be gauged. Because the symmetries which can't be gauged are just the elements in the co-kernel of this map. There are things which are down here which you can't hit with the map from the gauged ones to the ungauged ones. And here are two examples. I already gave you one. It's an odd Dirac monopole. Also turns out if you try to gauge the rotation symmetry of a fermionic tennis racket, you can't do it in a consistent way. And again, that shocks me because that ought to have some simple physical argument why. Okay, so here's my summary. What I've done is I've hopefully turned topological actions, which are somehow, at least to me, were very arcane. There were many constructions and they seem to be all over the place in the literature. Now there's a machine, an algebraic topology machine, which allows you to calculate them and actually really understand where they come from. And I think one of the obvious physics applications of that is to use it to study strong dynamics using anomaly matching in the way I've described. I've been pretending all along that this is a classification. That's not strictly true. But the reason it's not strictly true is because I passed to homology at a certain stage in the argument. And what you really need to do to get all the actions is you need to study Bordism. And actually what you need is the so-called differential version of Bordism. That exists, and it's not exactly known yet which is the right version, but once the right version is available, then it really will be able to possible to just capture all topological actions in one go. Gauge theory, global symmetry, whatever you like. And my last point is that, as I said, what I think is really interesting about this approach is that it's really just the first step in a long road in which you try to understand quantum field theories full stop. And today I've just done the classical part of it, the classical actions, or the semi-classical part, but the tools are now in place, thanks to the mathematicians, for taking this program further, and that's one of the things that I hope to be doing in the next few years. So thank you very much. I'm sorry that I've gone on for so long, but that I hope you've enjoyed it. I certainly have. Thank you.
Thank you very much, Ben. We're silent, of course, in our clapping, but you can appreciate the audience. Let me throw it open to questions.
Ben, can I ask you something?
Questions.
Yes, please.
In your last slide there, when you had an X, which was just a solo point,
yeah,
and you still have maps from X to M, do you?
The other way around, maps from M to X.
M to X, yeah, and M is the thing that has dimension N.
M is the thing that has dimension N. M is your space-time, but of course there is only one map from a manifold to a point.
Yeah, but on the subject of equivariance and these differential cohomological setups, I don't know if you're familiar with a paper about 18 months or 2 years old by Mueller and Szabo, where they have a kind of equivariant functorial approach, and they take Dirac-Witten theories and they construct or examine obstacles to gauging a global symmetry. It's a kind of functorial version of an earlier paper by Thorngren and Kapustin.
Yeah.
So the equivariance is kind of put into the functorial approach there, although it is very hard work to verify their formulae. Yeah,
so I said it sounds like there's some link there, so I should definitely check that out.
Oh, you haven't seen that?
Yeah, I'm familiar with the one by Thorngren, but I'm not familiar with the one by Mueller and Szabo.
Well, it's more or less no new results, except they can deal with a non-abelian group in the case where Thorngren and Kapustin can only deal with an abelian group. And also
the gauge group is non-abelian, is it?
Yeah, well, you have D, and then you have G, and you extend it to an extension.
Yeah.
A short exact sequence. Their D can be non-abelian.
I see.
So they have a non-abelian co-cycle for the extension, but it's only a technical detail. The ideas are all the same.
Okay, thank you.
But it's interesting.
Mm-hmm.
And these formulae, I don't know if these are new. The progression from n to n+1 with R over z and z. What quite is new there?
Oh, here there's absolutely nothing new. I mean, this is, like I say, this is the Bockstein sequence.
Yeah.
In cohomology, and this is de Rhams theorem.
No, but the thing that you said that you didn't see in Dirac or Witten or
sorry. The thing which is certainly extremely well known is this classification of Chern-Simons terms in odd dimensions, Digraph-Witten.
Yeah.
What I haven't seen, although like I say, it's pretty obvious, is a classification of theta terms in even dimensions in QCD.
Yeah, but for finite groups, these are the same. So
in finite groups, absolutely, yeah, but this is true for any compact group.
Yeah, so that gives you a clue to what you're doing.
Yeah. Yeah, so in finite group, these are the same, yeah, indeed. Yeah.
And so those papers I quoted are dealing with discrete groups.
Okay.
Because it's Digraph-Witten.
Very good.
Discrete and finite.
Very good. Okay. But
and
these results
in most of the cases, but not all.
Yeah, good. So these results are true for any compact G.
Yeah, sure.
Yeah.
More questions?
Can I have a question that you mentioned?
Yes.
You mentioned like higher categories, but can you maybe give a easy example of a 2 category which relates to this? Because like 1, it wouldn't be enough, but like 2, saying how 2 categories appear.
Yeah, so the point is that when I extend this notion of extended locality, is I need to, so that the geometric picture of quantum field theory, the functorial picture, is that I have a source category, which is a Bordism category, and historically just consisted of basically objects were n-1 manifolds, and Bordisms were n manifolds with boundary going between the two. And that would be sent, quantum field theory as a functor, and it would send the objects to vector spaces, and it would send the morphisms to linear operators on vector spaces. And the place where higher categories enter is as follows. It's now not sufficient, because of extended locality, to define the theory just on manifolds with boundary. I must also define the theory on manifolds with boundaries on corners. And then there comes the question, and corners of corners and corners of corners and so on. And then comes the question, so clearly now I need to associate a category to this thing itself. And so that's where a two category enters the picture. I should say that because of this...
Why do you need a category here? Because like corners, they can be treated as some kind of singularities or whatever, and there is a theory how you treat like orbifolds or some more general spaces.
Well, it's just that I need to be able to compose, I need to be able to, if I start with a closed manifold, I need to be able to cut it along manifolds with corners. And then there comes the question, this is a functor, what does it associate to a manifold with a corner? And the answer is it has to be a two category.
Okay.
I mean, actually, I should say this whole issue of smoothness, when you build in smoothness, in fact, you need not just a n category, you actually need an infinity category. But the breakthrough of the last 10 years has been to basically formulate these things in a way which looks like the correct answer for this setup of Bordisms.
Okay, thank you.
Again, Domenico, you have a question?
Yes, hi. So you mentioned at the beginning of your talk about the symmetry protected topological phases.
Yeah.
I was wondering, because actually there are a certain kind of SPT which are fermionic, and usually people classify them in terms of super cohomology. So basically, Z2 graded algebra cohomology. So I was wondering, in your picture, you can naturally extend, right?
Yeah, so the correct picture, as I said, is that what you need to do is you need to add an extra structure, which is spin.
Yeah.
Which I didn't have, I had an orientation. And you need to pass from, remember I said I just have homology, you need to pass to Bordism. So the conjecture is, and it's certainly not known to me yet exactly how to do it, is that there is an analogous diagram in differential spin Bordism. And what will happen in that diagram is things which were just cohomology groups will be replaced by spin Bordism groups. Because these are cohomology and Bordism is a homology theory, these will actually be Anderson jewels of spin Bordism groups. So you'll have things here, you have, like, roughly speaking, this thing here will be the Hom from Bordism to U1. And this is exactly the thing which, spin Bordism, this is exactly the thing which has been used a lot in the recent literature to classify anomalies. And this is why I said that there's a connection between topological actions and anomalies. The thing which appears here in 1 degree higher will be this Anderson jewel of spin Bordism in 1 dimension higher. And that's the thing which is being used, at least by some authors, to classify SPT phases.
Yes, yes. But also there are some conditions, because in order to get the spin structure, one has to really, for instance, there are conditions on the Stiefel-Whitney invariance, right? So
yes, but I have already fixed that by insisting on spin Bordism.
Okay, that thing. Yeah. Then I guess you can also move to spin C structure.
All of these things. And the point is that differential cohomology works in exactly the same way as generalized cohomology. So anything that you can, any generalized cohomology theory can be lifted to a differential cohomology theory. And so you just need to decide which is the right one for the structures that you've got in play, whether it's spin C, whether you've got a gauge group present, and so on. Okay. And these are things which they've only been really known for the last few years, but it's known that for every single one of those cohomology theories, there exists a corresponding differential cohomology diagram. I'm not saying it's unique, and that's part of the reason why I haven't already written a paper saying what the right one is. They're not unique, and so you need to work out what the things are which appear down here.
Okay. Thanks.
But there is a story that it should be possible to tell.
Okay. Thanks.
Can I ask a quick question, Ben, about if you have different differential structures in the target space X, For example, you give an example where the target space was a torus. I presume you could get different topological actions with different differential structures.
You could. I actually had, one of my collaborators is a pure mathematician, and I had the great idea of using this tool of differential cohomology to study exotic smooth structures. And so the answer to your question pragmatically is yes. The answer to my question, whether you can actually use this thing to study from a mathematical point of view exotic structures, is basically, it's hopeless. The reason it's hopeless is there's almost as much information in differential cohomology as there is in just saying the manifold in the first place. You see, one thing which is known is that you can classify a manifold, that is to say its diffeomorphism class, just by telling me all of the functions out of that manifold. And I already told you that in degree 1, differential cohomology is all of the functions, smooth functions, from the manifold to U1. And so you're in a classic situation in algebraic topology. If you want to try and actually understand something, you need to make an invariant which is coarse enough so you can actually compute it in a useful way. And the problem with differential cohomology is it's basically not coarse enough. But to answer your question, it is a diffeomorphism invariant, and so it will care about different smooth structures on your target.
Thanks.
Very good. Other questions? Bal, are you happy?
I have to think about it. I don't fully follow. I'll read his papers.
Any other question before we? Then let's thank Ben again. I will stop the recording and we can go to an informal discussion. Okay. Excellent. Thanks, Ben.
Thank you.
Bye.